Okay, so we're in chapter 12. This is where we start in Calculus 3. Chapter 12 is not going to have any actual calculus in it. What we need to do is start to familiarize ourselves with three-dimensional space. Since up until this point, you wouldn't really have had much need to work in three-dimensional space in previous math classes. But that's kind of where a lot of the work that we do lives in this class. So we're going to start from the basics, specifically 12.1. We're going to introduce a three-dimensional coordinate system. And so up until this point, you've been working primarily in what we call two-space or Euclidean two-space. And two-space is just two-dimensional space. That's what we mean by that. We use this symbol to represent two-space. I'm going to be reading this as just R2, but it's kind of this thick capital R shape. We call that blackboard bold. R2 is the symbol that represents two-dimensional space for our purposes. And the way that we work in two-space is we introduce a coordinate system that allows us to plot points, and then being able to plot points allows us to create curves from functions and things like that. But in order to plot points, we need two axes in two-dimensional space, an x and y axis. That's familiar territory. Three-dimensional space, which we're going to be calling either 3-space or symbolically R3, has to introduce a third axis in order to have that third dimension present. So we're going to call that the z-axis. Now, here's a picture of the x, y, and z axes. Typically, we think of the x-axis as coming out of the page. Whenever I hand draw these axes, I'll usually make y completely horizontal. X will be on a slant, but you want to think of that as coming out of the page. And then z is typically oriented upwards, the way that it is here, vertically upwards. Just like in two-space, the intersection of the axes, the coordinate axes, is the point that we call the origin. We're going to symbolically represent that with a capital O typically. Now, something that you get in three-dimensional space that you don't get in two-space is what we call coordinate planes. And coordinate planes are just a plane that contains two out of those three axes. So you can see in this picture where the coordinate planes live. Notice the xz plane contains the x and the z axis, hence the name xz plane. And then we also have an xy plane down here, a yz plane over here. Okay. We'll oftentimes reference these planes for some of the work we do later in this chapter. In addition to that, if you think about two-dimensional space, we think of the two axes, the x and the y axes, as splitting or partitioning two-dimensional space up into four distinct quadrants. You deal a lot with those quadrants in trigonometry, for example, when you're learning the unit circle. In three-dimensional space, we think of the three axes as dividing space up into 8 sections that we call octants. There's 4 of them above the xy plane, 1, 2, 3, 4, and then 4 of them below the xy plane. We can number them the way that we do with quadrants in two-space, but we tend to not really worry about which is which, with the exception of the first octant. The first octant is the octant that's determined by the positive x, y, and z axes. So actually, I just realized we didn't really talk about which part of these axes are positive, which are negative. The part of the x that appears to be coming out of the page is the positive x-axis. The y-axis the part of the y-axis that points towards the right, that's the positive y-axis, and the part of the z-axis that points upward is considered to be the positive z-axis. Okay. So with that said, let's look at plotting points in 3-space. So here we have an example of just an arbitrary point ABC that we wanted to plot. Notice that points are represented by ordered triples. These coordinates correspond to specific values from each axis. So A is the value on the x-axis that we use. B corresponds to our y-axis. C corresponds to our z-axis. Okay? So in plotting points in 3-space, it's a little bit tricky because you're trying to plot a point in 3-dimensional space, but on a 2-dimensional page. And so if we were just to put a point where we think it belongs, it's a little ambiguous where that point really is. So typically, if we're just plotting points in 3-dimensional space, we give it some guidelines to be able to see a little bit more clearly where that actually is. So the way we do that, we start by finding A, whatever A happens to be on the x-axis, and then from there, B corresponds to the y-coordinate of this point. We can get to the, or we can kind of align ourselves with that y-coordinate by moving in a direction that's parallel to the y-axis, which is what this line right here is doing, a total of B units. And then C, whatever C is, it corresponds to a value on the z-axis. So that's our z-coordinate. We would move parallel to the z-axis from wherever we ended here to get to that point. So you can see how this sort of maps out a little route from the origin to that point. And by drawing these lines in, it's a little more clear to see where that point actually is. Now, one thing we could also do is add additional lines parallel to these different coordinate axes to create a box. And this point right here would represent one corner of that box. So in this example down here, we're going to do the same thing. Here we want to plot the point -4, 3, 5. -4 is our x coordinate. So notice our x-axis is the one labeled x here, and the negative x-axis goes back into the page. So we'd go back 4 units to get to -4. Our y-coordinate is 3, so we move in a direction parallel to the positive y-axis, which is this direction, 3 units. And then -5 is our z-coordinate. If the positive z-axis is the upward pointing part of the z-axis, then the negative z-axis is pointing downward. So we're going to move down 5 units to get to -5. Here. So these red lines here are following that path from the origin to the point that we want. And then again, these additional lines drawn here just kind of give it a little bit more depth, so it's easier to see that that point is really kind of the opposite corner of this box here. Okay, so that's a little bit on plotting points. It's fairly basic and straightforward, but especially if you're not artistically inclined like myself, it's tricky to sometimes, draw in 3 dimensions, so it just takes a little practice. Okay, now when we talk about points in 3-space, a really important term, I guess, is projection. We use the idea of a projection a lot in this course for different things. So what we mean by a projection is if you were to take some point, in this case the point is A, B, C, in 3-dimensional space or 3-space, and if we were to drop a perpendicular from that point to any one of our coordinate planes, then wherever that perpendicular would intersect that plane, we call that a projection. And one way you can think about it is if you were to take that point and shine a flashlight on it in a direction that's perpendicular to a coordinate plane, then the projection of that point onto that plane would be the shadow that it creates. Now notice, in each of the coordinate planes, let me go back here where we have them labeled. In each of your coordinate planes, the xz plane, for example, all of the points in the xz plane have a y-coordinate of 0. In the yz plane, all of the points have an x-coordinate of 0. And you can probably guess in the xy plane, all of the points have a z-coordinate of 0. Whichever variable, what's called variable, is missing from the name of this plane, that's the coordinate that's going to be equal to 0. So that idea is key in understanding how to find projections of points. So for example, if I have this point ABC, some arbitrary point in 3-space, and I'm looking for the projection onto the xy plane, well, that means I'm pushing this point, or I'm projecting this point onto the xy plane, sorry, that's down here, in a manner that's perpendicular. So that means I'm not changing the direction of the x in any way. I'm not changing the direction of the y in any way. So my x and y coordinates aren't going to change. They're going to stay a, b. But the z coordinate is being brought down to 0. So the projection of the point A, B, C onto the xy plane is a, b, 0. And you can see here it's similar for the other planes. Whichever variable, whichever letter is missing here, that coordinate becomes 0 when we talk about the projection of that point onto that plane. Okay? So points are important to know how to plot those, interpret coordinates and whatnot, and they're also extremely boring. You know, there's nothing terribly interesting about plotting points. You think about algebra, you learn how to plot points, but more interestingly than that, you learn how to graph functions, you know, lines, parabolas, things like that. We want to be able to do that in 3-space also. So we start from the idea of an equation. You know, how do we graph from an equation? And we're going to start with some of the simplest graphs that we come across in 3-space. But the key thing to understand in 3-space when we're working in 3 dimensions is that graphs of equations generally don't look like curves. We will encounter curves in 3-space, and we're going to see that it's easier to understand those in the context of vectors, which we'll talk about in the next section. But in general, equations tend to give us these things called surfaces. So a surface is an intuitive concept. You probably know what I'm talking about when I say a surface. But here's a couple of the simplest examples. So for example, the equation z equals 3 is a plane. Just like in 2-space, if we are talking about an equation in 2 variables, if any of the variables in that coordinate system are missing, we assume that they just are free to vary. They can take on any value. So basically, when I say this equation z equals 3, I'm talking about the set of all points that have a z coordinate of 3, regardless of what the x and the y coordinates could be. It's not difficult to see that would look like a plane that intersects the z-axis at 3. So here's an image kind of showing you that. Similarly, if we wanted to graph the plane y equals 5, it's going to be a plane that's parallel to the xz plane and intersects the y-axis at 5. And in fact, anytime I deal with something that looks like x, y, or z equals a constant, what you're going to end up with, graphically speaking, is a plane that's parallel to one of your 3 coordinate planes. Okay, those are the simplest types of surfaces that you'll encounter in 3-space, but it's going to be helpful to look at some others. So here's 3 equations that I'd like to attempt graphing, and here I have to hand draw everything, so you get to kind of laugh at my artistic skills here. So I'm going to start with this one here. Let me start by creating my coordinates. Notice I'm making my y-axis horizontal, so I'm going to label that y, x, and z. Okay, now let's think about how we would graph something like this. So first of all, x squared plus y squared. In fact, I'm going to give myself some negative axes to work with too. Okay. X squared plus y squared equals 4. That should be a familiar looking equation. We normally in 2-space would recognize this as a circle centered at the origin with a radius of 2. And when I say 2-space, I specifically mean the xy plane. Well, we still have an xy plane in 3-space. It's just part of 3-space. So if I think of x squared plus y squared equals 4 as the circle centered at the origin, which is here, with a radius of 2, and living in the xy plane, I don't like where I put that negative 2, let's bring that in a little bit, then I have this circle that I'm not drawing terribly well, and that's in the xy plane. However, that's not the graph of this equation. It's only part of it. Notice that because we're in 3 space, all 3 variables would normally be present in an equation. But as was the case in those planes up above, if one of the variables is missing, we assume that it's free to vary. So that means z can equal anything. And what does that do to this circle? Well, if you can imagine this circle as being translated or moved up and down parallel, or kind of along the z-axis, almost as if the z-axis is like an axle, and this this circle is like a wheel. You know, what that does is it traces out this cylinder. Looks like this, and it goes down as well. And yes, this is not a good picture at all, which is why you'll notice I tend to gravitate more towards pictures that I can print than ones that I have to draw by hand. But you're going to have to draw some by hand, so I'm going to draw some by hand with you. Okay, next equation right here. So in this case, the equation looks the same as the previous one, but then there's this extra equation sort of tagged on, and this is just an additional restriction. So we already know what x squared plus y squared equals 4 looks like. Again, it's a circle centered at the origin with a radius of 2, x, y, z. Only this time, we have this added condition that says z equals 2. So that means that we're looking for the set of all points that satisfy both of these equations simultaneously. That means I couldn't put the circle in the xy plane, because remember, in the xy plane, z is equal to 0, and we need z to be equal to 2. Let's put that up here, 2. So now what I'm doing is I'm looking for a circle that's up here. Okay? And it's just the circle this time. Z is no longer free to vary, so it's not going to trace out that cylinder this time. Let's look at one more. This is a type of restriction that we'll encounter a lot later on in the course, where we have some equation that determines a surface and then an inequality that puts a restriction on what part of that surface we actually sketch in our graph. So x squared plus y squared equals 4. Again, if it were just this equation, we'd be talking about this cylinder that we drew over here. But now, even though z is allowed to vary because it's not z equals some constant, we do have this condition that says that z is bounded by -1 and +1, inclusive. So that means we're going to end up with something that looks similar to this first graph, but only a part of that cylinder. It's not the whole thing anymore. So let's draw this out. If we were meeting in person, instead of online like this, I'd be using GeoGebra for a lot of the graphing that we do. GeoGebra is free online, and it has a 3D grapher, which is kind of handy to have. So I made this a little bit bigger, but again, we have this circle that we use as our kind of initial guide here. Center of the origin in the xy plane, radius of 2. And now, this is 1 and this is -1. We want the part of the cylinder from this first graph that only goes from -1 to +1 on the z-axis. Okay, and again, my pictures tend to look pretty awful, so you just sort of have to bear with me on that. Okay. Here's another example. This time we're sketching a surface. You'll notice I already gave you the graph here. This is the from an example in the book. It's another plane. Notice this is a plane, but it doesn't look like a variable equals some constant this time. It's the surface y equals x. Why would this also be a plane? Well, let's think about this for a moment. Again, the z is missing here. So let's just focus on the x and the y. What if I wanted to graph this equation in 2 space? X, y. Well, I know that the equation y equals x is a line with a slope of 1 passing through the origin. It looks like this. right? Well, that exact same plane, the xy plane, remember that lives in 3 space. It's a coordinate plane in 3 space. And right here is that line that we sketched here. But what does the addition of the z-axis do to that graph? Well, again, the line that we sketched is now free to vary, which means, or the z coordinate of all the points on that line is free to vary, which means that line can be translated vertically up or down to create a plane. A plane is what you get if you take a line and then translate it up and down like that. So this image I copied from the book, and it's a little bit misleading. It makes it look like the plane only includes the positive x and y values, when really the plane actually extends this way as well and below the xy plane. So there's more to it than what we're seeing here. Okay, I think that's a good stopping point for this first video. We'll start looking at distance formula in 3 dimensions in the next video.